moving, but yeah, it moves.
There we go. All right, so let's go ahead and get started. So thank you everybody for coming to the 7th colloquium this semester at Augusta University. And this week we have the pleasure of having Dr. Valeria DePavia here to give us a presentation on linear logic. And she is currently a mathematician and computer scientist in California, working on a new startup in Berkeley called the Topos Institute, which is pretty cool and exciting. She's worked for places like Samsung as a principal scientist and Nuance Communications when she was a senior applied scientist, doing things related to computational linguistics. Is that right, Valeria?
Yeah.
Yeah. And so she's done lots of cool things in lots of different areas, especially in category theory and applications to logic, and done a lot of work on diversity in these fields, founding things like Women in Logic, the Women in Logic workshop, lots of really cool stuff. So I'm really excited to have Valeria giving us a presentation today. And so take it away, Valeria. Thank you.
Well, thank you, Harley. Thank you very much for this invitation. Hello, everyone. Good morning, good afternoon, whatever. Kind of depends on, I mean, for me, it's 10 a.m. But I know that for some of you, it's already in the afternoon. So hello. I think I wanted to start, as I was saying, I'm also at the moment remotely visiting the Department of Informatics in PUC RJ, which is my original alma mater. So I kind of should mention that there, which is cool stuff because I'm working with the guys in the Laboratory of Advanced Collaboration, which it does with mobile stuff. And it's very exciting to have contact and do research with some young folks doing kind of mobile communications. And thanks very much, Harley, for the invitation. Harley and I have been working together for quite a few years, and we've met in 2012 live in Vienna in one of the Flock meetings. And as I say, we have lots of things that we work together. And for a while, I was thinking maybe I should talk about some of our stuff to show the younger members of the audience that, it's perfectly okay to work with someone and have slightly different versions of the same talk. People bring their own background to the work that they do together. And, I expect some of you must have heard Harley talk about some of our work together. And I wanted to show that, there's always a slightly different version of talks and stuff like that. But then I decided that I wanted to try something different. So I am actually talking about work with two groups of people. So the two left pictures are from friends in Brazil. And there is one extra person because I couldn't find a picture, just Gisele and Elaine are the two more to the left. And Carlos Olarte in the middle is one of the friends that I'm working with on this work on linear logic. And Paul Terral is is my newer collaborator. And it's I want to talk at the end of something that Paul just talked about a week ago in ICLP, International Conference on Logic Programming, I think. Because because it's a new thing, but that is at the end of this talk. And they are all extremely good friends. And of course, I am very grateful to have this kind of international collaborations with people. Paul is at University of Texas, UNT. So this, and I'm not very good at giving references in these slides. I'm sorry about that. But so, this talk is based on these two papers. The ILLTP Library for Intuitionistic Linear Logic that Elaine presented in Flock 2018 in Oxford in the Linearity and TLLA workshop. And as I was saying, this deriving theorems and implicational linear logic that Paul just presented a week or 2 weeks ago. So, and the other thing I was thinking is that I wanted to talk about things that were easy for people to understand. Feel free to interrupt me and say if you don't understand things. I think it's much nicer to have a two-way conversation if people feel like it. I mean, I'm perfectly fine also talking for lots of times if people let me, but it's nicer when people interrupt and ask questions. So I wanted to do something a little bit easier than some of the work that we do in programming language that can be a bit forbidden. So I wanted to talk about this idea that there are things that we do in computer science that are that make computer science look very much like a trade, an apprenticeship, as opposed to science. And one of them is to benchmark things. So, if you have lots of tools for doing a particular task, I know most of you kind of for doing a CS course or something like that, kind of, normally you need something for some particular task, and you go to the web and you try to find all the things that do that stuff that you want to do, and you want to kind of compare them. And there's loads and loads of people that actually make this comparison between tools, their life work, and they actually earn a living doing these things, particularly for appliances and computer programs and stuff like that. But when you do it within a more academic setup, the idea that you have is that you want to measure performance in as impartial and scientific manner as possible. So that's the way I'm thinking of benchmarking. And benchmarking for theorem provers in particular is a well-developed area of artificial intelligence, AI. So it comes kind of almost at the same time as AI. I mean, people consider the birth of AI in 1956, the famous conference in Dartmouth. And at the same year, logic theorist was presented, and it's considered the first artificial intelligence program. And it was, oh boy, I've forgotten to put New and Simon's name here, but New and Simon are those guys, and they proved the first 38 theorems of Principia Mathematica, the famous work of Bertrand Russell and Whitehead. So it's been going on for a long time, and it is kind of a niche subject within CS, because by now we have several theorem provers. Some of them are interactive and some are automatic. So some people want to press a button, give it a problem, press a button and have a reply coming yes or no. And for that, you have to have slightly easier problems than the ones that when you have interactive theorem proving, where a human can help a little bit, can, for instance, give induction hypotheses and stuff like that. So, there's pros and cons of interactive and automatic theorem proving. You can try to use both of them, both kinds of theorem proving techniques in different areas, but for all of these things, you have lots and lots of theorem provers, particularly nowadays with GitHub. You find that everyone can create their own and kind of put it there, and it can be the best one for you, for your problem, for the stuff that you are trying to do. And because of so many theorem provers, there's been attempts at kind of measuring them in a scientific and impartial way, as I was mentioning before. And that's the life work of Jeff Sutcliffe in Miami University. And they have, since 1993, I think, been doing both this so-called CASC competition, which is the CADE ATP system competition, and this language of TP called Thousands of Problems with Theorem Provers. And this is a growing concern. Things are getting better. There's more theorem provers and stuff, but that doesn't happen so much for other logics that are not classical logic. There's several variations in the competition for things that are systems that specialize in different strategies, for systems that specialize in different domains. There's some big domains or smaller domains. There's quite a bit of variation on this competitions and on the things that people do for this annual competition. But as I was saying, there's not much for non-classical logics. But there is at least the ILTP. I think it's Jens Otten is the person that comes to my mind, but there's another two guys that are associated to that, so that I forgotten the name now. And that is about intuitionistic logic. And there are two other libraries of problems for model logic. QMLTP is one of them, but there's another one that I, again, don't remember very much, but I remember talking last year to Alexander Steen about it, and I think it is important. Most of CS is becoming much more data-driven, and we want to have logic being treated as seriously as other subjects. So we want to know how to have it data-driven in the right way. In particular, some of us, Harley, myself, and lots of other people, Paul-André Mélier, who kind of talked to you recently, and lots of other people, would like to have linear logic considered one of the things that we have good collections of theorems about, that we know what is true and what's not true, and under which conditions things are true and are not true. So the motivation for this work is putting linear logic in this kind of map, in the map of the automated theorem proving. So my goals were to collect problems and theorems in linear logic, but in a different way from most of the work that I was describing in the previous slide. I'm not so interested in efficiency of provers and the shaving seconds of how long it takes to prove a theorem. It's not my main concern. I want to investigate variants of the logic. Linear logic is a logic that's very different from the logic that people normally learn in the first years of CS, or that you actually learn from from high school and stuff. So I wanted to explore this difference between normal logic and linear logic. So I want to investigate variants of translations between logics in general. And so I wanted to use provers that, as I was saying, people are developing more and more by themselves. I want to use these provers as tools for experimenting with logic. So I want to make logic a real lab science. That's the reason why I decided that that was a better talk to give to you guys. I think it's a cool idea to think of logic as a lab science, a science where you have notebooks and you do experiments and you compare your experiments with the guy sitting next to you, experiments. And I'm afraid that we are far from that in many ways. I'm not saying that we've got there. No, not at all. But it's first steps in this direction, and I think that is a good direction for us. So you might be saying, but why linear logic, Valerie? What you kind of, why bother with kind of going for a different, relatively recent logic instead of doing the more traditional things? Why don't we kind of keep to the systems that we know and love? Well, we do keep to the systems that we do and love. There's loads of work on that. There's several conferences, several sets of competitions doing classical logic. But some of us think that linear logic is an extremely precise and very deep tool for semantics. So let me tell you a little bit about linear logic, because I don't know how much the audience in Augusta kind of knows about linear logic. I expect some of you haven't even heard about it, and it's always kind of fun to go over what I consider the important points of it. So the linear logic is a proof-theoretic logic, so it's something that pays much more attention to the proofs than to the fact that something is a theorem or not. So that's different and interesting. And the basic idea of the logic itself is that assumptions, when you're doing your proofs, cannot be discarded or duplicated willy-nilly, kind of without thinking. Only some assumptions can be duplicated or discarded, and for these assumptions, you must mark them with a sign, in this case, an exclamation mark that Girard decides to read as "of course." And what we the simplest models to understand this difference were produced by Girard in terms of cigarettes and Marlboros and Camels and stuff like that. But this kind of metaphor is a bit outdated nowadays. So I'm going to do my metaphors with cappuccinos and lattes, because, you know, maybe the rest of the universe doesn't care about coffee and cappuccino and latte, but personally, I'm very fond of them, and I kind of think it's worth thinking about it. So the assumptions or hypotheses here will be used just like dollar bills. And we kind of think about this use of assumptions as accounting for logical resources. Now, you might say, well, it's only, I mean, this is happening since 1986. You know, in one hand, it's too long ago, because we don't tend to think about things in the past more than 5 years nowadays. But on the other hand, you might say, no, but for logic, this is very, very recent, right? You know, logic is going on since Aristotle's days, kind of 2,300 years ago. And so why not kind of talk about the normal things? But so, you know, I was going to say that it's not that recent. Many logicians, including the ancient Greeks, kind of thought about some of the issues of resources in the reasoning that we do. And in particular, I think many people from the Greeks on kind of have wondered about this idea that when we say that something implies something, that actually we mean that the first thing, that if A implies B, that that we actually have to use the A to produce the B in some ways. So this notion of relevance between antecedents and consequence in logic, in normal logic, has been a worry of people forever. In particular, in the 50s, lots of people came up with this idea of relevance logic, a logic that pays attention to this connection between antecedents and consequence, and between making sure the conditionals were not unrelated like they are in tradition, in what is now traditional logic, Frege and Russell's logic. And the relevance logic kind of had a bit of a movement, but they didn't have one thing that I consider essential. And this is that, you know, the logic of Boole, Russell, Frege, and all the other guys that kind of came and made the huge movements of the beginning of the last century, and that kind of created all the things that we call mathematical logic nowadays. All this work, it's very important, and we want to keep it as part of our arsenal of tools and methods as much as possible. So one of the things that linear logic has that the relevance logic guys didn't have is this, it comes with this translation that transforms a normal implication that we deal with in mathematical logic, as everyone knows, so A implies B on the bottom of this slide, it can be transformed into a linear logic implication so long as you add this operator, of course, the bang in front of the A and linear implication in B. So it's a little bit of this business of having your cake and eating it, because you are trying to think about resources by using your linear implication, but you can always go back to what you had before with the normal implication using this translation. So as I was kind of indicating a minute ago, we have this simplified and kind of just for fun things like, if you have $1, you can have a linear, that linear implies a latte. And if you have $1, you can linear imply a cappuccino, but you only have $1. So you can conclude either your latte or your cappuccino, but you cannot have both of them with a single dollar. And that's the kind of very superficial kind of phenomena that I want you to have on the back of your mind whenever you see this little symbol of implication that we call the lollipop, or lolly for the friends. And as I was saying, in usual logic, you don't pay attention to uses of premises. So if you have an A implies B and your A, the core of logic is that will give you a B, but you still have your A, you don't lose it. So total trivial things that you can do about it. If you have a traditional implication, you have A and A implies B, you get a B. As I say, that's the main, to my mind, the main thing of logic in general is this ability to apply implications to arguments and get the conclusion of the implication. And as I was saying, you can reuse your A, so you also can deduce an A and B. With the linear implication, you cannot do that, so you cannot reuse your A, so you can get your B, but the A has been spent, has been used, like your dollar bill when you get your latte. And that kind of makes a collection of changes in the rest of the logic that, if you're not very used to think along these lines, you might not realize. So in particular, it will give you two conjunctions, a conjunction where you can discard a B, which is what we write like this little circle, this little hat, and a conjunction, a linear conjunction where you cannot discard any of the conjuncts. And you have this bang or of course operator, which allows you to put back in the logic the possibilities of reusing and discarding. Now, we have loads of linear logic results, and for a little bit of sociology, this, as I was saying, was introduced around 1986. And for some 20 years, lots of people kind of thought, whoa, I can deal with that. This is kind of cool. I can produce lots of things for that. So lots of models were created, soundings and completions for these models, and kind of lots of interesting work. But also lots of people kind of complained that that it didn't do as much, that linear logic didn't do as much as they wanted to do. I think it's fair to say that nowadays it's not as growing as a field within computer science as it was before. But another big thing of linear logic was this idea of focus systems, which I'm not going to talk much about, but it is part of the papers that I mentioned, particularly the first one, and it's another very important idea. So I think we had some 30 years of limelight, but I think it's kind of not so important nowadays. And then you say, well, then why do you bother with these benchmarks for linear logic then? I think one of the reasons I want to bother is because it's very useful in programming language, and it produced lots of ideas within programming languages and game semantics and quantum physics and stuff like that, and linguistics. And for most of these fields, the applications are not of the whole of the system of linear logic, but they are some of the ideas in the system. And I I don't know if you know the pictures over there, but the first one is Rust, the language that was created by Mozilla kind of fairly recently. The second one is Clean, a language coming from the Netherlands. And the third one is Granule, kind of Dominic and Harley and others kind of new ideas using an extension of linear logic ideas, thinking about how to consider this operator, the Pling operator, the of-course operator, a more sophisticated view of this Pling operator. But I don't know much about it, and I'm not going to talk about it at all. But I think, in any case, this idea of having the several provers and of linear logic itself, the basic vanilla language, and discussing how different variants affect the provability of stuff or not is an important idea, and that's what I kind of wanted to do. Is, as I say, I want the benchmarks to help us understand the logics, where they differ or not from traditional systems, not to understand the provers, not to discuss how to make a prover better or faster or more efficient. I'll let that for the other friends. So here are some linear logic provers. As I say, there used to be many more than that. The only one that's reasonably recently in this list, I mean, actually, the top one is kind of is the one that's in my work of Carlos Olarte and Elaine Pimentel and Gisele Reis. It is a totally vanilla prover, trying to use as little as possible the tricks of the trade, because Turing provers kind of have lots of tricks of the trade, which we don't want to use. We want to think about it as simplified as possible. The YALA is just a deep embedding in Coq, because Coq is one of the big Theorem proving platforms in the world nowadays, perhaps the biggest one. And it's by Olivier Laurent, who is kind of has a similar attitude to mine of kind of trying to think about the logic as opposed to the Theorem proving techniques. But on the other hand, he is kind of fully committed to Coq, and hence there is a series of differences. And there is plenty of newer versions coming up. But we don't want to think about the provers as much as about the theorems and what we can say about them. So let's think about the problems then, right? To be used as a standard for checking how things compare to each other, a collection of problems should satisfy some criteria. And these are some of the criteria that I kind of thought, and the friends kind of, we all thought together that would be necessary. So first thing is that the formula should be able to distinguish different characteristics of the logical systems and provers. So you should be able to show you where design choices in the systems are natural. It should be able to tell you important theorems of the logic, things that we think are characteristic of the logic and how it differs from traditional systems. And should be large enough so that you can do some comparisons between different provers and the systems, hopefully. And again, for people who are doing kind of more real theorem proven, you should kind of be able to do automatic comparison of scripts and efficiency. And you might want to do things like ensembling of provers and stuff like that. But as I say, will not be taken in consideration here. On the business of design choice points, you have to admit that's a difficult point to make, because what you take to be the basic system will depend on who you're talking to. So this is kind of still very much up for debate. So I'm going to show you my design choices, right? I think there is a big design choice between classical linear logic and intuitionistic linear logic. And kind of lots of people disagree. Lots of people think that intuitionistic linear logic is a a silly subsystem that you should just think about classical linear logic. Because for other reasons, I think that's not the point. I think much to the contrary, I'd prefer to think about intuitionistic linear logic by and large. As I was saying, there's differences in provability. And I think there isn't, as far as I know, a set of principal LL theorems, but it's up to debate again. I think it's easier to think about the intuitionistic, it's easy to transform intuitionistic theorems into intuitionistic linear theorems using the translation. So that's an easy place to find the theorems. So I can take and I will take all the library from the guys who did intuitionistic logic and translate them into linear logic, and that will give me lots and lots of theorems. But instead of just doing the ILTP and translating those guys into linear logic theorems, I wanted to translate initially the theorems considered by Kleene, because they are the traditional logical things, right? It's the way that from the 1950s onwards, everyone learned mathematical logic was using Kleene's textbooks. He kind of wrote very textbooks full of exercises and stuff like that. So it's kind of nice. It's nice to think about the fact that he the theorems that he has in his book, Introduction to Mathematics, are theorems that he thought would be important for his students over several years to learn, so that they could understand what was happening in a logical system. So that's why we start from there. And, as I say, we used the original theorem of Girard to create this translation, but there are many other translations that have been produced in the last 30 years. And then you have to say to yourself, which one do you want to choose and why? And as I was saying, the point here is to try to clarify the theory, and all this choices will be important for us. So this, normally when you see pictures of Kleene in talks and stuff, he looks very serious and like a military guy that he was when he was young. So I decided to put a picture of him looking like a fun-loving guy. It's the only one I know that looks like that. The other ones look very strict. And
it's the same one that I've been using in my theory of computation lectures.
Good. It's a good one, right? It looks kind of as if he's having fun doing his stuff. And he has this basic collection of intuitionistic and classical terms. He's teaching classical logic, but because he's a good mathematician, he always kind of makes this gives you this extra information. For these guys, I don't need to use classical logic, and for these guys, I do. And I think kind of our thought by using the original Kleene things was to help to uncover bugs and sources of unsoundness in the theorem-proving machinery, because that, at least originally, because originally in 1995, I started doing this with Sarah Calvala, using the theorem prover Isabel, which is, together with Koch, one of the big frameworks for proving theorems kind of automatically. But I'm afraid our version of it is deprecated now, and I don't think there is a new one. I think no one did a new version of linear logic in Isabel. So if people want to do it, please be my guest. That would be nice. And thinking about this business of between classical and intuitionistic logic, we kind of decided to stay with this rudimentary fragment of intuitionistic logic, which is implication in intuitionistic logic, negation, and conjunction. And why this fragment? Oh, because intuitionistic disjunction poses some problems. You have to decide whether you're going to go additive or multiplicative disjunction. And of course, I would say we should go for the multiplicative disjunction, but then, you know, you have this business of a classical multiplicative disjunction or intuitionistic multiplicative disjunction. This will lead to very different systems. And also because, you know, because we want to keep in mind all the time the connection to category theory and the fragment of intuitionistic logic that has only implication, conjunction, and negation corresponds directly to Cartesian closed categories, and that is on the back of our minds. So taking this fragment, we have only 61 theorems in Kleini's book, and you can look at all these theorems retyped in PTP in our GitHub repo that's down there. And this is the picture from the book itself, looking at things. So, you know, you can, I'm sure the library of Augusta University has the traditional book. Now, what about the translations? And here it's the business, you know, it's a good thing about working with several people is that people will have different directions and interests. And, you know, I wanted definitely the Girard translation that is called Up G over there on the 4 translations. Other people wanted to play with the second Girard translation that was introduced in the same paper in 1986, but that I don't know why we're calling lazy. I mean, I know why we're calling lazy, but I don't know why we're calling it K. But you know, there's the idea that of course operator goes outside of the implication. My friend Elaine was a student of Dale Miller, and she likes very much theorem proving in the style of Dale Miller. So there's the Liang and Miller's 01 translation is number 3. And I kind of wanted also to have something that's not a real translation, it's just a forgetting the intuitionistic structure and reading the implication as being a linear implication, just to see what happens to the theorems that are not theorems once you kind of forget structure in linear logic. So, you know, if you take the 61 theorems of Kleini's and multiplied by 4, because you have the 4 translations, you have 244 problems. And, you know, it becomes far too big. Give me an automated theorem prover, please. So Carlos kind of joined us and implemented, Carlos Olarte. So he implemented a very basic prover for intuitionistic logic, as well as a focused version of ILL, which stands for intuitionistic linear logic, and normal LL focused. And that is implemented using rewriting logic and, rewriting logic and mod, a traditional theorem prover that Jose Messinger and others started in SRI kind of quite a while back. And when you kind of do this trivial things of looking at this stuff, we end up kind of, I need to go a little bit further. So this is the 61 in the 4 translations. And, you know, you can start seeing things, you can start seeing patterns and stuff that we haven't yet exploited or explored. And that's why I wanted to give this talk too, because I think there's quite a bit to be done, not only with the 61 theorems that are kind of laid bare here, but also with the other ones that we, on this level there, when you look at the red ones, you see the red ones are things that are actually not provable because they are kind of things that required intrinsically contraction and weakening. And this is kind of, this connects very strongly to reverse mathematics, this idea that you want to know where you need this kind of hypothesis to prove a theorem. So, you know, there's plenty of stuff to be done here, but kind of for people doing theorem proving, this is too tiny, 241 is too tiny. So we extended this basic collection using translations of all the problems from the ILTP. And even if, and that was not enough either, so kind of Frank Fanning was very kind and suggested this idea of looking at the Petronets repository. And there's a traditional result connecting Petronets to theorems in intuitionistic linear logic. And so reachability in Petronets corresponds to provability in a fragment of intuitionistic linear logic. So we end up in total with 4,494 formulas in our linear logic, intuitionistic linear logic library. This is enough for some comparisons, and there is enough for us to start thinking about patterns and non-patterns, but we need much more. And then, you know, this is where I was kind of, this project was presented in the linear logic workshop in 2018 in Oxford. And apparently didn't get a very good reception. I was doing the, as Harley was saying, I was doing the more diversity thing on that day. I was in the Women in Logic, and I didn't see our paper being presented, but I've heard that there was I'm sorry, I think I'm talking about the next slide, about the lukewarm reception, but let me kind of go over first on these things, that what we actually have at the moment. So we propose a set of linear logic sequence tests, and we have this implemented for provers for LJ, ILLL, and CLL. All these provers are focus-based. We take focusing as a basic mechanism for proving things. And we tried these 4 translations. And, you know, we are trying to see now is patterns on the timeouts and the failures, because I didn't show you properly, but so apart from the red things, you can also see these little clocks, which are timeouts. So, you know, it might or it might not correspond to complexity issues. And this is the kind of thing that we haven't investigated yet, and I would like to investigate. So, you know, the point is, can we see patterns on these timeouts and failures? Can we see other patterns with when we have bigger sets of theorems that we are investigating? Can this help when comparing translations? I don't think these translations, I mean, I think we got the 4 translations that we got there just because, you know, each one of us wanted one. But there's other translations that we didn't think about. And, you know, I don't have any theory of comparing translations. I would like to have one of these. And I would like also to do this business of parallel and ensemble provers to see how much it is the mechanics of you know, of this. Carlos, who is the guy who implemented this himself, says that, you know, he didn't put any effort into making this a good theorem prover. He just said, let's go basic and easy, as basic and as easy as possible, just using what the theory gives us. So, you know, it's kind of always a difficult thing to discover what is the technique and what is the logic that we're implementing. And I would like very much push this work forward. But as I was explaining a minute ago, we had this lukewarm reception. There's not much interest in the benchmarks from the theorem prover guys themselves. They are mostly interested in specific applications, and then they kind of want to use their theorem prover for whatever they want to do. And lots of them are actually thinking about automating proofs in logic itself. So there's quite a bit of work on that, and thinking of different embeddings of linear logic into Coco or into Isabel and Agda and things like that. But so there's much more of a internal facing preoccupation, less of a preoccupation with how other people need theorems or not need theorems, how much they understand of the theorems or not. And as I say, my co-authors all want to do different things. All of us have different interests in things that we want to do. And at that stage, I kind of got to read Paul's papers on test generators for propositional intuitionistic logic. So that's not linear. That what Paul was doing in 2019, and here there are two papers of his that are kind of very interesting papers and not so easy to read, at least not for me who don't speak Prolog as a first language. But the thing that Paul does is to think about generator functions. And he kind of generates automatically lambda terms. And because we know that we have the Curry-Howard isomorphism, the lambda terms, or closed lambda terms, correspond to theorems. So he said, oh, then, I'm doing theorem proving in a different way. And I then kind of came to him and said, well, can we do the same for linear logic then? Can we use the generator functions that you produce to rewrite them, paying attention to when things are used and not used? So when to do them for linear logic. And okay, we are getting there, guys. So this is the changing gears. That is the second paper. So this is the work in ICLP. And as I was saying, the main insight of this work is that instead of building formulas and trying to prove them true or false, we build only the true linear formulas. And Paul was building only the true intuitionistic formulas, implicational intuitionistic formulas before in 2019. And there are 3 papers of his on that. So, it's not a triviality to kind of, I was very happy that when I said to him, let's try to do it for linear logic, he didn't say, oh, go away, you can do that if you want, I'm busy. Because there's lots of things to do with the intuitionistic setup too. But instead, he kind of got excited about the idea of doing it for linear logic because there's a different size of linear logic that comes into play here. We will rely on the Curry-Howard isomorphism the same way as he was relying on it for intuitionistic logic, and we'll generate all theorems of a given size. The point is that we use this idea that inferring types for a lambda term that you know is closed by construction, it's not so hard. You can use in intuitionistic logic, you can use a version of Hindley-Milner, and when you're doing that for linear logic, it's even easier because you have more constraints. You know that any variable has to appear once positively and once negatively, and if you don't have that, then you can throw it away. It's not going to be a provable theorem of linear logic. So this business of inferring a type from a type, inferring a type for a term is easy. Going over the Curry-Howard isomorphism, as Paul says in his papers, and coming back again, you can end up doing the hard thing, which is to find a witness for a theorem, because you can find it's not that you can find, by construction, you only thinking about the things that inhabited the types. So you end up kind of having a collection of terms and types that you can pair up, and that are all and only the theorems of intuitionistic, propositional, implicational, linear logic. So what do you get assume for a minute that we could do it. So what do you get if we did that? Well, we get an implication intuitionistic logic prover specialized for linear formulas. We also get a big data set for training neural networks to then prove intuitionistic and linear theorems. And our very preliminary results, which are not in this ICLP, are very good indeed. So we have a very high success rate using very off-the-shelf systems of neural networks, sec to sec. So as I was saying, the intuition is that we're using combinatorial generation of lambda terms, which Paul had done before. We're using type inference, which is an easy problem, to solve type inhabitation, which is a hard problem. So this is the point of the paper as it exists at the moment. Now, I'm kind of going to read to you a little bit about this stuff, but I have a few problems with that, and that's okay. So to create the implicational linear formulas, Paul tells me that there's a fairly simple Prolog code, and that we end up with binary trees of size n counted by Catalan numbers. And then Paul is not the only one telling me that. There's lots of other work along these lines. Both Noam Zauber and Pierre Lescan kind of had the same sort of idea. And they end up being, and that is the surprise, and kind of, if you go and watch Noam's videos, he has 2 videos on explaining mathematics, where he shows this business that the binary trees of size n really are kind of associated to the Catalan numbers and to this interestingly named A289679 in this database of interesting numbers in mathematics, interesting sequences in mathematics that who is the guy who kind of done that? I'm sorry for them. I don't remember his name, but this guy that has a huge community joined this guy into creating this database of sequences that are interesting, and they are interesting because they show up in different bits of mathematics. That's the OEIS. And the fact that, the implication linear formulas are done by that. Paul has done quite a bit of work to show that these things can be considered Motzkin trees, because you enforce this one-to-one mapping from the variables to their lambda binders when you're doing linear logic. As I was saying, you have to have the closed linear lambda terms because you want the theorems, not derivations in general. And then you have this chain of refinements that you can read in the paper that derives this compact and efficient generator of pairs, a linear lambda term in normal form and their type, which is the theorem. So the theorem and its proof. And lo and behold, completely by magic, as far as I'm concerned, you have almost 8 billion terms in a few hours. And this is all in GitHub for anyone to play with it as much as they want and to kind of complain if things don't work. Mostly to Paul, because I won't understand the complaints at all. But, it's just there. So anyone who kind of doesn't agree or thinks that there's a mistake, I'm very interested in hearing from them. As I say, I think it is working fine because the other guys were doing similar things. In particular, Pierre Lescan was doing counting without creating the term. So we have a very concrete bijection between we use this Motzkin trees to connect a theorem to its lambda term. Pierre Lescan was just counting the number of trees in the lambda calculus, and he kind of finds similar numbers, but he doesn't manage to get as many as us, I think because of implementation issues, because he says that he only gets to n equals 6 or something like that, and we get to n equals 8 kind of in this first pass that Paul has produced, and you can look at these things. So maybe you're saying to yourself right now, oh yeah, this is too fast for me. Yep, it is too fast for you and it's too fast for me too. And as I say, it's all based on old results of Gregory Mintz and Zyberg results that were based on Mintz too. And they are simplified in the linear implication case. So our main future work now is to see if we can extend it to linear nonlinear logic, because we want to have, so, Paul has this 2019 papers on implicational intuitionistic logic. We have together this 2020 paper on intuitionistic implicational linear logic. We want to put the two together to see if we can get even more theorems. And on this hopeful note, I will kind of say thanks and wait for questions. Thank you very much.
All right, thank you, Valeria. We're all kind of virtually clapping. I had one question with respect to how you're modeling using the Catlin numbers and stuff like that. How is the of course modality done in that?
Sorry, say it again.
Yeah, I was trying to understand. You were talking about how you used the way of modeling the system using the Catlin numbers and the binary trees, right? Like a subset, a restricted version of that.
You cannot see the modality, the of course modality there. Right?
Okay.
It is all kind of in the wash, as they say. It's a bit like S and K combinators. You can't.
Right.
You cannot see where it is. So it's the putting the two together is not a total triviality because of that.
Yeah, exactly. Yeah, that's what I was thinking.
I mean, that's why it's future work and not something that, an easy
yeah,
work.
it's definitely not going to be simple, right? There was another one on the chat here.
Yeah, that's, if you didn't have time to copy the link to the repo, right. Sorry, what is this repo, Clement? No, it's all about propositional logic. Who's asking this? Achka asked, are all these theorems propositional? And no, we are only dealing with propositional logic at the moment. Nothing about first order. First of all, because first order in linear logic is kind of not such a interesting thing normally, but also because this is work that's kind of normally in the side burner, kind of not main work of any of the 4 people or the 5 people involved. I actually kind of discovered this paper of Paul's because I was talking to him about work on language. He has completely different work on language, and so I kind of went to his scholar profile to try to read his work on language, and I said, hey, this looks interesting. It connects to this other stuff that I'm doing with Elaine and Carlos and Gisele, so kind of that's how it come about. Famika is asking some question. Hi Famika, how are you doing? Given one of 4 or more translations, is it possible to say something like, if a proof of phi takes n, then a proof of t phi takes, I don't know if that's true or not, Famika. I don't know if there is a uniform factor. I don't think so, because the translations are very different. The Liang and Miller translation is very different from the others. And even the 2 Girard translations are very different one from each other as well.
Yes, but one per translation? One factor A for one single translation? Would that be possible?
I guess.
It somehow reminded me of work by Harold Schellings. Is that correct? Or?
Oh, yeah, it's just very much, I mean, I'm still trying to understand Harold's work this many years later. I think in this, and actually in my slide I mentioned, I mean, there's an LK TQ at the in one of the slides that I just showed, which is exactly Harold's Tet and Q translations. Elaine tells me that she understood it all and that it's okay, but I have not understood it completely yet. Well, that's the pleasure and the trouble of working with other people, right? Other people have different competencies, and you want to get their competence in your stuff, but sometimes you get a little bit left behind, kind of, as you can see from my talk, I'm still trying to understand lots of the stuff that Paul kind of can do and that I cannot understand yet. And of course, I don't think Paul is so interested in trying to make the connection to category theory, but I am, right? So, the question that Harley just asked is something that's important to me. How do we separate the things, and if it's possible to separate the things? So there's another question from Ruben. So the implication fragment is decidable then. Is this an old result? I'm interested then if there are known combinatorial results about the proportion of terms of a given size. Well, one of the things that I discovered doing this work, which I did not know before, Ruben, is that actually I have to find the reference to give you because, but it exists, is that theorems of intuitionistic logic and theorems of classical logic, the difference between them is getting smaller as the numbers grow bigger. So they are not as far apart as I thought they were before. In the long range, they end up kind of apparently. I mean, some people have done proofs to show that they actually tend to kind of get together. And I thought the implicational fragment being decidable was not an old result, but I'm very bad with complexity. So, I might be misremembering or misunderstanding. So I think the people who kind of did quite a bit of work on implicational linear logic only were Nat Shankar and Pat Lincoln and two other people from SRI, I think, a while back. And I think I need to check. I don't know for a fact, Ruben. It's combinatorial results about the proportion of terms of a given size. Well, there is more than I knew until this work, but I don't know. I don't know the whole thing. And, I have a feeling that what happens is that proportions of terms of given size, if people have done work on that, is in classical logic, not on intuitionistic or linear in any case. But take it as it goes, just as I mean, I don't know for a fact. I'm just giving you my personal best guess.
Sure, thank you. Yes, I mean, that could be an interesting thing to look at then, I guess.
I can send you later or send to Harley this result about the terms of intuitionistic logic and classical logic and ending up the same place, tending to each other, because I was very shocked when I saw that. I was saying, well, that's just, because, if you're coming from the algebraic background, you kind of, the Nishimura lattice kind of terrorizes you, right? It's just there on, the one I mean, the one that shows the indecidability of intuitionistic logic, the thing that goes kind of going up, and it's in the, so, that thing always made me think that there was a big distinction between classical logic and intuitionistic logic. Elaine does know her things, and in saying MLL is decidable. The thing that's still a little bit debatable here, Elaine, is this business that we're not taking the we don't have the disjunction, the multiplicative disjunction, right? We only have the implicational fragment. But I mean, if you know that that's okay, then I'm happy. As I say, I know nothing about the complexity, so I'm always having to rely on my friends for that. Cool. So any other questions? I mean, I think this idea of looking at translations in general and trying to see what can we tell about different translations, that's a very open problem too, right? I have not seen any work done on that. I would like to know more about it.
Yeah, same. I'm glad you're working on this because I think it's going to end up having some very useful results coming out of this. Because I'm looking at a lot of these different things too as I look at these new systems based on the graded stuff that you mentioned earlier. I'm wondering a lot about things about translations and different subsystems, and so I think it's going to be very useful.
So that's what Clement was posting, right? Was the repo for the graded, or I mean, I don't.
No, I think it was just the link for one of the theorem provers that you had on your slides.
Okay, thank you.
LLTP.
Yeah.
Yeah. Just for other people if they wanted to look at it, I think.
That's great. Thank you. Much appreciated.
Excellent. So if anyone doesn't have any questions left, then we'll all be done.
Right.
All right. Thank you so much, Valeria.
Kind of thanks for talking.
Yeah, it's great seeing you and great talk.
Thank you. So see you in the next one, and kind of at some stage, I think I should talk about our joint work too.
Yeah. No, but I thought this was great because I haven't had time to look too much at this that you've been working on, so I was happy to be able to hear about it. So
great. We need help. People kind of wanting to think about this. At least I need help. People wanting to work on some of these things. Kind of please get in touch because, as I say, there's lots to do as far as I'm concerned. Super. Thank you, guys. Thanks very much for the nice thank yous and everything. Bye-bye.